morning, everyone. So last class we have looked at the history of neuroscience, and also hope you enjoyed the workshop. Hope some of you were able to attend the workshop. So this class I'll cover a bit of mathematical background. Particularly, you need a lot of data from neural network from dynamical systems. All right. So we'll start with linear dynamical systems, and then move on to nonlinear systems. It will take a couple of classes. So let us first start with eigenvalues and eigenvectors. So if A is a square matrix that is of size, that is if A is a member of the set R n by n, then the eigenvalue equation is given by this equation. So X is an n-dimensional vector. It could be a complex vector of dimension n. Right. Then the this eigenvalue equation, and to find the eigenvalues, this equation you need to solve. Determinant of A minus lambda I equal to 0. So this becomes a polynomial called the characteristic equation. Right, and so you solve that, you get the eigenvalues, then you plug the eigenvalues back in the first equation, the eigenvalue equation, then you get the eigenvectors. So for a square symmetric matrix, the situation is somewhat simple. You'll always, so think for any square matrix, a real matrix, or even a complex matrix, you always have n eigenvalues. In general, they can be complex, right? But you may not always have n eigenvectors. There's some theory behind that. There are some matrices called defective matrices where you have n eigenvalues, but you may not have all n eigenvectors. Okay, but for square symmetric matrices that given by A transpose is equal to A, life is simple. You have n eigenvalues like always, and also you have n eigenvectors. And also for symmetric matrices, the eigenvalues are real. So let us look at an interesting theorem. So if A is a symmetric matrix, real or complex, if it's real, we call it a symmetric matrix given by A transpose is equal to A. If it is complex, if the elements of A are complex, then you say A star is equal to A, because when you have a complex matrix, when you take a transpose, you not only transpose the elements, right? And that is Aij is equal to Aj. You also take the conjugate, right? So that is like your A prime Ij is equal to Aj star. Okay, so for the new matrix, right? So for Aij is equal to Aj star. Okay, just 1 second. So Aij is equal to Aj star. So sometimes, therefore, transposition of a complex matrix or a is also called transjugation. Okay, because it involves both transposition and conjugation. But anyway, we won't bother about all that. We'll assume that always whenever we talk about transpose, conjugation is implied. Okay, so whether A is a real matrix or complex matrix, A transpose means doing the appropriate thing, depending upon whether it is real or complex. So the complex symmetric matrix is called Hermitian matrix or Hermitian. So now there's a nice theorem that says eigenvalues of a Hermitian matrix are real. So Hermitian in complex and symmetric in case of real. So how do you prove that? Take the eigenvalue equation X equal to lambda X and multiply by X transpose on both sides. So you get X transpose X is equal to lambda X transpose X. So on the left side, X transpose X means mod X square. So the norm of X square. Oh, sorry, on the right side. On the left side, you have this. So now if you take transpose on both sides, you get X transpose X, right, or X transpose X. On the right side, you'll have lambda star because this is a real number. Mod X square is a real number. So conjugate is still the same. So therefore, X transpose this is X transpose X, right? So both are the same. So therefore, so this is equal to this. Therefore, lambda into X mod X square is equal to lambda sin mod X square. Therefore, lambda is real. So therefore, for Hermitian matrices or square symmetric matrices, the eigenvalues are all real. So similarly, for skew Hermitian, or what is defined as A transpose is equal to minus A, the eigenvalues are purely imaginary. So how do you show that? Again, start with the same eigenvalue equation. X equal to lambda x and multiply by x transpose on both sides. X transpose x equal to lambda x transpose x, right? And then take transpose on both sides. So that will be again x transpose A transpose x is equal to lambda transpose, actually lambda star, which is same thing as star, mod x square. So therefore A transpose is minus A, therefore that minus comes out, right? And this is mod x square. So therefore you get lambda is equal to minus lambda star, right? So which means lambda is purely imaginary. Right, now there's a third theorem about the eigenvalues of a matrix called orthogonal matrix. If Q is an orthogonal matrix, then it is defined as Q transpose, its transpose is its inverse. So therefore Q transpose Q is equal to QQ transpose is equal to I, the identity matrix. For such a matrix, eigenvalues lie on the unit circle, that is mod lambda is equal to 1. So how do you show that? Again, start with the eigenvalue equation, Qx is equal to lambda x. If we take a transpose on both sides, x transpose Q transpose is equal to lambda star x transpose. That because this is a scalar, I mean it's a complex scalar, x lambda. X transpose, x is a vector, so it becomes x transpose. So now multiply these two equations. Okay, so then you get this equation. X transpose Qx is equal to lambda lambda star xx transpose. Xx transpose is mod x square. Q transpose Q is this I, so that disappears. So you get mod x square is equal to lambda lambda star, that becomes that becomes lambda mod lambda square, right, times mod x square. So mod lambda square is equal to 1. So which means that the length of the complex number is equal to 1, which means lambda is of the form e power I theta. The theta is a real number. So what you see here is, if I just have to summarize the three theorems, right? If A is a Hermitian, so this is real, this is image. So A is symmetric, okay. And if A is skew-symmetric, the eigenvalues on the complex side, and this is on the unit circle, or A is orthogonal. There's another theorem about symmetric matrices relating it to orthogonal matrices, which says that for any symmetric matrix A, there exists an orthogonal matrix Q such that Q transpose AQ is equal to a diagonal matrix consisting of all the eigenvalues, right? That is, so this is a matrix, you can call it D. So where D is given as this diagonal matrix, lambda 1, lambda 2, lambda n, and all the other terms are zeros. So how do you show that? So again, let Qi and lambda I with eigenvectors and eigenvalues, right, corresponding eigenvalues of the matrix A. That means AQI is equal to lambda AQI. Now consider the matrix defined, let's consider matrix Dij, which is given as Qj transpose AQI, right? Sorry, AQI. So now AQI is lambda IQI from the first equation. Therefore, this becomes Qj transpose Qi lambda IQI. Now lambda is a scalar, so I can bring it out. So this becomes lambda I Qj transpose Qi. So now Qj transpose Qi, if I is not equal to j, this is 0 because Qj's are all orthogonal, they form an orthogonal system, right? And so therefore Dij is equal to lambda I. If Qj and Qi are the same, j and I are the same, then they are of unit length. So we have Qj transpose Qi is equal to 1. Therefore, Dij is equal to lambda I for I equal to j, otherwise it's 0. So therefore, this is a matrix, this is a diagonal matrix with the eigenvalues on the as the diagonal terms. Now let us construct the orthogonal matrix using all the eigenvectors like this. Right, so that means QIs are all column vectors, So imagine you just assemble them like this, and you construct it n by n square matrix. Then you can easily show that Q transpose, if this is what Q is, then Q transpose AQ is equal to this D. So simple algebra. So now if you bring Q transpose and Q to the right side like this, what we show here, right? A is given as Q into D into Q transpose. So if you expand out D a little bit and also expand the capital Q matrix in terms of the component eigenvectors, you get A is equal to sum of lambda I QI transpose. Right, so QI transpose is actually a matrix, and this is called QI transpose is a, if it is a real thing, it's a matrix R n by n, and this kind of a product is called an outer product. It's a product of a vector with itself. Normally product of a vector with itself, we know the dot product, which is called the inner product, which gives you a scalar as output. But if you multiply two vectors, a vector with itself, or or two different vectors of same dimension but like this, you get a matrix, and that's called an outer product. So you can express the matrix A, where A is a symmetric matrix and Q is a corresponding orthogonal. There's an orthogonal matrix, right? Then you can express matrix A as a linear sum of the outer products of the eigenvectors, which are weighted by the eigenvalues. Anyway, this is called the eigen decomposition of A. Okay, so now with that background, let us come to dynamical systems. Right, why are we talking about what is a dynamical system? Dynamical system consists of a system in which has a state vector x, okay, and so I can, which is n-dimensional. So x is in Rn, right, and this is some coordinate system x2, x3, etc. So this system varies in time, starting from some initial condition. That variation is described by a differential set of differential equations. So that's a dynamical system. Any system in which there is a state vector x, which is an n-dimensional vector, which varies through time, starting from some initial condition, and that variation is defined by a set of differential equations. That is called a dynamical system. Now, why are we studying this in the context of the brain? Because brain is a dynamical system, because it has all these properties. It has it's a network of a bunch of neurons, and each neuron has some kind of an internal state, and that state keeps changing with time. Right? We'll describe all that better when we look at the neurobiology, look at the biology of neurons. So therefore, and then we'll describe that variation using some differential equations. So therefore, it will be interesting to understand first, how do you describe those systems in generic terms mathematically? Then we'll see what are the specific equations for brain and for neurons. Okay, so the dynamical system is given by this generic equation dx by dt, x is a vector, dx by dt is equal to f of x, right? And so how you study this is you first look at what are called stationary points, right? And that is points where dx by dt is equal to 0. So then you look at, so let us say dx by dt is equal to 0, that is the point where flow is 0, at some point x equal to xs, right? So then we'll only, so thing is, let us say, so what this equation gives you, the first equation 1 gives you is, at every point x, right, dx by dt tells you how x will change in the future. If you are here, it will change like this. If you are here, it will change like this. If you are here, it will change some other fashion. So at every point, what this differential equation tells you is, if you are at a given point x, its variation is going to be in some direction. The dx by dt tells you how x is going to vary. Right? So you'll have a vector field. This defines a vector field. There will be some points where typically there will be some points in the vector field where the flow is 0. Okay, so there can be a point like this. Right? It goes outwards, but if you are at that point, there is no flow, you will stay there. So at that point, you say that the dx by dt is equal to 0, right? And that's equal to f of x. So you can solve for f of x and see where it becomes 0. Because it's convenient to find out such points and analyze the flow around that. So we'll see all this later. I'm just giving you the big picture right now, but we'll come back to this later. So to analyze the flow around that point, where dxdt is equal to 0, flow is 0, such points are called stationary points because there the system is stationary, it doesn't move. They are also called critical points, fixed points, equilibrium points, and so on. So there are different names for that. So now we'll study how the system varies around that point. But to do that, what you do is f of x is generally a nonlinear function, typically. But you linearize that function right around that point, and so define something like aij is equal to fi x by dou xj, because x is an n-dimensional vector, right? So if you want to linearize, you want to find the derivatives of x of f. So f is interesting function. So let me call y equal to f of x. Okay, so x is in Rn. We have just seen the table. What is y? Y is dx by dt. Since x is an n-dimensional vector, dx by dt is also an n-dimensional vector, right? And therefore y is also an n-dimensional vector. So therefore y is in Rn. Therefore f of x is also in Rn. So f of x here is what is called a vector function. That is, it takes a vector as input, and output is also a vector because f has an n-dimensional vector as input. Its output also has n components because output is a vector y. So anyway, let us start with a linear dynamical system, which is given by dx by dt. I'm just saying that this can be obtained, derived from a nonlinear system by linearizing around it. But I'll get back to this concept later and describe it in more detail. So dx by dt is equal to ax, and so this is x dot. Okay, the dot is shifted slightly. There's some problem with the, I think, software. So x dot is equal to ax, right? So now this you can expand out into any equations like this. X dot has n components, so I can write it as x1 dot, x2 dot, and so on. On the right side, you can have a11 into x1 plus a12 into x2, and sorry, this x should be here, not a subscript, okay, and so on and so forth. Okay. So basically, it is x1 dot is equal to a11 x1 plus a12 x2 plus etc. And so on. So xn dot, so the bunch of equations like that. Xn dot is equal to an1 x1 plus etc. Plus ann xn. So like this, you have a set of n linear differential equations. So this is a linear dynamical system. So how will you study this? What is the solution for this? Let us start with the simple case of n equal to 1. So I have a one-dimensional system. So dx by dt is equal to ax. So x is a real number, so it's a scalar. What is the solution for this? So we all know that the solution for this is simply this, some constant c times e power at, because if I differentiate this, dx by dt is equal to a into c into e power at. So this is equal to ax, right, which is equal to a into e. So this is, so therefore you get c is equal to x naught. C is the initial condition. The solution is very simple. What is the solution for the more general case of n is greater than or equal to 1? Yeah. So for the general case, the solution is given by this formula. So here for 1D case, solution is just a scalar times some e power at. For the n-dimensional case, it is so general solution will be of this form: a scalar which can be a complex number c1 e power lambda 1 t times q1. Q1 is a vector. So if A has to be a square matrix, so here we assume it's a square matrix, right? Sorry, so this is A is it's a square matrix, right? We can see that here the way we expanded it. If A is a square matrix, it will have some, so A is R n by n, and assume that it is yeah. So assume that it has all eigenvalues and eigenvectors. So these are the eigenvalues. Lambda are the eigenvalues of A, and Q are the eigenvectors of A. Therefore, they satisfy this equation. AQI is equal to lambda AQI. So solution xt is c1 into e power lambda 1 t q1 plus etc. plus finally Cn into e power lambda n t Qn. So this is the complete solution. So we need to find out what C1, C2, C3, Cn are, but this is a complete solution. So how do you prove this? You plug in this expression into this equation, and this is original equation 1. So what do you get? So calculate x dot of t. So you get, all the lambdas will come out, right, when differentiate, because this is C1 is a constant, Qis are also constants. So you get sum over I of Ci lambda I e power lambda I subscript I t times Qi. Okay, so now lambda I Qi, if you take this expression, here you have lambda I Qi, okay, which is nothing but AQi. We have seen that already here. So if you plug this in here, the lambda AQi becomes AQi. So you get C into e power lambda I t AQi. So A can be taken out, right? So you get this part. And what is Ci lambda I t Qi? That is nothing but the original expression x. That's why you plug this back in. So x dot is equal to axt. So we recover the original equation number 1. So we have proven that this expression here is a solution of the equation 1. So now let us consider the behavior of this solution, right? So you can see that first of all, if you consider the points x dot equal to 0, right, and then look at the behavior of the system around those points, we'll find out if this point is stable. So the system behavior around that point is stable. Secondly, we'll also classify, so such points are called fixed points, also called stationary points and critical points and so on. Let's use around fixed points. So we'll classify the fixed points based on the behavior of the system around the neighborhood of the fixed point. Here in case fixed point is origin. Because if x dot is equal to ax, right, so x dot is equal to 0 when x equal to 0, right? This it's but even if x is not 0, x dot can be 0. That's a different matter, right? Because if x is in the null space of A, that's a different matter. But if x is 0, x dot is definitely 0. So x is 0 is definitely a fixed point of the system, right? So now what we'll consider is a fixed point, that is the origin, is it stable, and then what is the behavior of the system around the origin. So let us look at that. Let's come up with some classification results. So to do that, first we will take a simple two-dimensional case, because easily illustrate by drawing some pictures, but it can easily be generalized to n dimensions. So sorry, this should be subscript. So let us take a two-dimensional case, n equal to 2. Then the solution is of the form xt is equal to c1 e power lambda 1 t q1 plus c2 e power lambda 2 t q2. So now q1, q2 are eigenvectors. They are orthogonal to each other. Let us assume they are orthogonal to each other because A is symmetric. And lambda 1, lambda 2 are eigenvalues. So, and for even further simplicity, right, let us assume that q1 is along x1 axis and q2 is along x2 axis. Obviously, in general, it's not true, but we can always rotate the field. I'm not doing all those steps, but we can always, I can just say for now that we can always rotate the field and make sure that the eigenvectors are aligned with the coordinate axis. Okay, so let us just take it as given for now. If you want, I can do a derivation of that later, how all that can be done. So now in this simple system, in simple situation, let us try to analyze the behavior of x in the neighborhood of the origin. So which means if this is aligned, this component, right, because vector x has two components. So something into, we'll call this, I don't know. So some p1 into q1 plus p2 into q2. Okay, so q2 and q1 are unit vectors. Therefore, p1 and p2 are the weights. These are the two components, right, of the vector. And q1 and q2 form an orthogonal system. They are aligned along x1 and x2 axis in this simple case. Therefore, I define x1 is equal to c1 into e power lambda 1t times times q1. So this is x1 component of it. X2 component of it is c2 into e power lambda 2t. Okay, so this is in the direction, right, q1, and this is in the direction q2. This is a component along these two directions. So now if x1 and x2 components of a vector are varying like this and this, how does x as a vector vary? Let us look at that. Now let us look at this answer to this question for various values of the eigenvalues. So take first case as a first case. Let's take the case where both eigenvalues are real, because they are real. They have to be real if A is symmetric, but they are negative. Both are negative. Then what happens? If both are negative, then x1 is equal to c1 into e power lambda 1t, which is a negative number. Exponent is negative. So x2 is equal to c1 into e power lambda 2t. So here also exponent is negative. So what that happens when that happens? If you start from anywhere in the coordinate system, somewhere close to the origin, right? Since both lambda 1 and lambda 2 are negative, x1 and x2 keep on dying, keep on decaying. So therefore, this point simply approaches the origin asymptotically, and then once it approaches the origin, it stays there. It will take infinite time because it's an exponential decay. So like that, no matter where you start from, so your starting point is defined by C1 and C2, because C1 and C2 are determined by the initial condition, as we have seen before in that simple case. So no matter where you start from, it will always go to the origin. So like that, right? From everywhere it goes to the origin. So if you draw a vector field of the system of a system like this, where the eigenvalues are both real and negative, it looks something like this. You see that all the flow is directed towards origin, and once it reaches origin, it stays there. If you start at the origin, because origin is a fixed point, it doesn't move. So not only that, if you start from the origin, it doesn't move, but if you get kicked off the origin a little bit, since all the flow is directed towards origin, you go back to the origin. So therefore, the origin is a stable fixed point. This is the definition of stability. That point should be a fixed point in the first place, and then if it is considered, if it must be stable, then if it is perturbed off that fixed point, it should come back to the fixed point. Then you say that the fixed point is stable. So when the eigenvalues are negative, real and negative, in that case, definitely the fixed point is stable, and such a fixed point is called a stable node, where you call it a node when the eigenvalues are real. When you call it when the eigenvalues are complex, you call it something else. So node refers to the fact that eigenvalues are real. Stable refers to the fact that eigenvalues are negative and the flow is pointed towards the fixed point. So any perturbation will correct the system and put it back, bring it back to the fixed point. Now the opposite happens when the eigenvalues are real and positive. So in this case, x1t is equal to c1 into e power lambda 1t, which is positive. So lambda 1 and lambda 2 are both strictly positive. Right. So then what happens is this is not exponential decay, but exponential blow up. Right. It blows up. So in this case,
Sir,
hello. Yeah.
sir, I have a question.
Yeah.
Sir, are we still under the assumption that A is symmetric?
Yeah. Correct. Yeah.
Then we don't have to mention that they are real, right? They will be real, no?
Yeah. Yeah. So I mean, I keep saying they are real. In the background, I just have stated that A is symmetric.
Okay. Yeah.
Okay. Then
Understood.
I'll. Yeah, that's correct. You don't have to say A is symmetric. But what happens is, typically when you take a nonlinear system and then linearize, and if it's a differentiable system, then you will get the Jacobian will be symmetric, and that's how you get a real this thing. But anyway, yeah, you don't have to say is square and symmetric.
Okay, sir.
Okay, so where are we? Yeah, so if you take x1, lambda is positive, so it's, no matter where you start from, it will blow up exponentially. The same thing happens with x2 also. So therefore, if you start from anywhere in the neighborhood of the origin, right, it will go outwards. So if you are on the origin, it's a fixed point, you'll stay there forever. But if you get perturbed, then you'll get thrown off and you'll go up to infinity. So therefore, this point is an unstable node. It's not because lambdas are positive, lambdas are real, and it's unstable because lambdas are positive. Then the third case is a mixed case. It's called a saddle node, where one eigenvalue is positive, another eigenvalue is negative. So in this case, x1, x2 are like this. X1 is C1 into e power lambda 1t. X2 is, right. So in this case, let us say lambda 1 is positive, lambda 2 is negative. So then x1 blows up. So it is, if I start from positive value, it will go to positive infinity. If I start negative value, it goes negative infinity. But x2 goes to 0. So therefore, what happens is, in one direction you go to 0, other direction you go to infinity. So if you look at this flow, the way it is written, right, x2 is going to 0, whereas x1 goes to either plus infinity or minus infinity. So this point is called saddle. In this case, again, fixed point. If you are here, you will stay there. But if you get thrown off, if I get thrown off in the along the x1 axis, right, I go to infinity. But if I get thrown off along x2 axis, I come back to the origin. Okay, so such a point is called a saddle node. Now let us look at the cases where eigenvalues are complex. Right, so lambda 1 2, since A is a real matrix, right, when eigenvalues are complex, so it will have the two eigenvalues will form complex conjugates. Sigma, therefore they are sigma plus or minus I omega. So therefore, the two components will be x1 is a real part of C1 into e power lambda, so e power sigma plus I omega t times t, and x2 will be also a similar thing. So more generally, it will be x1 will be a1 into e power sigma t plus cos omega t plus some phase phi 1 x1, that is x2 will be a2 into e power sigma t cos of omega t plus phi 2. So basically both are sinusoids, right, and the real part is negative real part. That means sigma is a negative number. So if you take plots of x1, it will be a decaying sinusoid, something like that. So the same story with x2. So therefore, if you plot them one against the other, x1 against x2, then you will have your trajectory will spiral, right? If you are at the origin, you will stay there, but if you get perturbed off the origin, you will spiral towards the origin. Okay, and so therefore, this kind of a point is called a focus. Focus refers to the fact that the eigenvalues are complex, right? And the approach is a kind of a spiraling approach to the origin, to the fixed point. And it's called stable because if you get thrown off the fixed point, you get back to it. So opposite happens when the real part is negative. So real part is positive, sigma is positive. So in this case, again, it will be just the same like before, but just that the amplitude is now positive and it will explode. It will grow exponentially. Right. So again, in this case, you will have two sinusoids, but this time it is exponentially increasing sinusoids. It looks something like that. And next two also will have the same form. So if you plot them one against the other, it will start. So if you are at the origin, you will stay there, but if you move off the origin, you will go away from that. Right, you will spiral outwards away from the origin. So this is called it's a focus again, but it's an unstable focus. Now something interesting happens when sigma is equal to 0. The real part of the eigenvalues is 0. That means eigenvalues are purely imaginary. So then if you go back to the expressions, what happens is a1 into e power 0, that is, this is 1. So amplitude doesn't change. So they are pure sinusoids, right? So both x1 and x2 are pure sinusoids. Right, so if you plot the one against the other, it will get a circle. Okay, so very interesting behavior. If I start from the center, from the origin, I'll stay there. But if I start from anywhere around it, right, I just go in a circle around the origin. Okay, so for the sake of a small exercise, I suggest you do a small exercise. So this is your equation x dot equal to x. Let a be equal to 0, 1, minus 1, 0. Can somebody tell me what are the eigenvalues of this equation, of this matrix? I'll give you a couple of minutes. Anybody? Hello, anyone?
Plus or minus 1?
Plus or minus?
1.
No.
Plus or
It's
minus
I,
iota.
plus or minus I.
Very good.
I, sir.
Plus or minus I. So lambda is equal to plus or minus I. So that's exactly what we're talking about. Purely imaginary eigenvalues. Two eigenvalues, both are imaginary. But since A is a real matrix, right, the two eigenvalues, the complex eigenvalues will be complex conjugates. So therefore, you have plus or minus I. And we have said that's exactly when you get a center, right, where both are pure sinusoid, x and x are both sinusoids. So let us try to expand out this equation like this. X1 dot, right, is ax, so which is equal to 0 plus x2. Okay, if I plug this in. So x2 dot is equal to minus x1 plus 0. I'm just multiplying this, right? X1 dot is equal to x, I'm expanding it. So can you clean up these two equations and combine them into one equation? So x1 dot is equal to x2, x2 dot is equal to minus x1. If I combine them, what happens?
x1
Okay.
double dot equal to minus x1.
X1 double dot is equal to minus x1, or x1 double dot plus x1 is equal to 0. What is this equation? What does it denote? Have you seen this before?
Simple harmonic motion.
Very good. Simple harmonic motion. So more generally, it is x double dot plus omega square x is equal to 0. So what do you have in simple harmonic motion? Simple periodic motion, right? And simple periodic motion, no matter where you, so if you have a pendulum like this, a good example of simple harmonic motion. If I start with a small amplitude, it will make small amplitude oscillations and keep oscillating. If it's ideal one without friction, it will keep on oscillating forever. If you start with from a large amplitude, right, it will have a large amplitude motion and it will oscillate like that forever. So similarly, in case of a center, if you start with a small perturbation, it will go around the origin in a small circle. If you start with a large perturbation, it will go around the origin in a large circle. Center is of great interest for us, a great preliminary interest for us, because tomorrow we'll be modeling neural oscillations, because neuron will keep on producing some periodic activity like this. Voltage which goes repetitively. I mean, it's perfect. It can be a perfectly periodic behavior. So center is quite appealing, right? Because this is a first equation which will produce some nice periodic solution. But the problem is center, this kind of equation is not a good model of neural oscillations, because In the center, the amplitude depends on initial condition. If you start with large amplitude, you will get large. If you start with large initial condition, you get large amplitude oscillations, like in case of simple pendulum. But in case of a neuron, that's not the case. Whether you start from a small oscillation initially or large oscillation, it will always go to the same amplitude oscillations. You can start from here, you can start from here, doesn't matter. After that, it will always go in the same amplitude. So that means to capture this late space. So in terms of if you draw it in 2D plot, if I start from here, I'll go to this circle. If I start from here, let's say, I'll go to this circle, and after that I stay on that circle. Okay, I start from a small value inside. But if I start from a large value outside, again I go to the same circle and keep going around. Why is that? Because the amplitude is always the same after one steady state is reached. Right, that's the kind of oscillation you see in case of a neuron. Whereas in case of a center, the oscillation amplitude depends on initial condition. Okay, so center, the good thing is it gives you a basic equation, basic model for periodic solutions. Right, so it is appealing, but we need to do something to this, some correction to this, so as to get a periodic solution of a different kind, which is more appropriate for a neuron. So we'll see all that later. Okay, so now let us keep on studying more examples. Right, but now both lambdas are real, but they are equal. Right, so both lambdas are real and equal. So lambda 1 is equal to lambda 2, and both happen to be negative. And lambda 1, lambda 2 are real. So then what happens? We go back to this formula, right? So both are real and both are equal. So which means x1 is equal to c1 times e power lambda t. X2 is equal to c2 times e power lambda t. So you see that x1 by x2 is equal to a constant. So which means all the flow trajectories are straight lines, because x1 by x2 is constant, and all those lines, flow lines, are straight lines pointing towards the origin, which is a very interesting case. This kind of a fixed point is called a star. So we're giving some names to each of these fixed points, and what is interesting is even in case of a two-dimensional dynamical system, which is linear, you get such rich variety of fixed points. You can imagine what kind of fixed points you can get if you have an n-dimensional system. Then finally, one of the lambdas is 0. That means, let us say lambda 1 is 0, lambda 2 is real, could be positive or negative. Okay, so then what happens? If lambda 1 is real, so lambda 1 is 0, then x1, if you plug it in here, it becomes a constant. X2 is this. So x2, depending upon the sign of lambda 2, because lambda 2 is real, it can either go up or go to 0. Exponential blow up or exponential decay. Right, but x1 is constant. That means no matter where you start from, your x1 will not change at all, but x2 will either go up to infinity or go to 0. Go to 0 means this is the origin. This is x1 axis. Either it goes out to infinity if lambda 2 is positive, or it goes to 0 if lambda 2 is negative. So this is called a line of fixed points. It's sometimes also called line of attractors. Okay, so basically in this case there is a line. So in the previous cases we found a point can be an attracting point or a repelling point. If it is stable, it's attracting. If it's unstable, it's repelling, right? In this case, it's a weird situation where the entire line can be a repellent, pushes away all flow away from it, or can be an attracting line where the entire line attracts flow towards it. So you can see that even in two-dimensional cases, you find such interesting cases. In n-dimensional cases, then you can have a whole subspace of fixed points or attracting subspace, where all flow can be attracted towards subspace. But we won't talk about that later. But it's good to know that these are the cases that are possible. So what we'll do, we'll take a short break now. We'll break for today. And tomorrow we'll take again the two-dimensional system, x dot is equal to x, where A is a real matrix having 4 components A, B, C, D, 4 elements. We'll solve for the eigenvalues and we'll see, right? We'll take 2 parameters, right? Assume that A is parameterized by 2 parameters. The 2 parameters are the trace of the matrix and determinant of the matrix. If we take these two as 2 parameters, how do the eigenvalues vary as the parameters vary? And we know that as eigenvalues vary, the dynamics varies because the fixed point type varies, right? And then we'll look at different cases and make a map of all these different kinds of dynamics. So basically what happens is, as you vary some parameter, the dynamics suddenly changes. That is, what was a stable node until then suddenly becomes unstable, and so on and so forth. You can find all these interesting cases. And in such a sudden change is called a bifurcation. Okay, so in dynamical systems, this is very important for us when we study neurons, because you see bifurcations happening all the time when you study neural dynamics. Take a simple example where a neuron is normally in something called a resting state, and when you pass some current and the current crosses some threshold, suddenly it starts oscillating, right? That means what was a fixed point, some kind of a stable node until then, suddenly becomes an oscillatory state, right? That's a bifurcation. Okay, so let us take, so the real equations for a neuron are much more complicated. Well, but let us get a feel for how such sudden changes in dynamics can take place by studying a very simple two-dimensional system, right? A linear system, because neural models are almost always nonlinear, right? So let us start with this very simple model and study how bifurcations can take place in a dynamical system. So let us get to this point tomorrow. Any questions? Any questions, anybody? Yeah, if not, then so we'll wind up for today and let's meet tomorrow. Thank you.
Okay, sir. Thank you, sir.
Thank you, Sanjay.